Hi, I'd like to do another example with you that has to do with RL and RC circuits, but this time I'd like to do an example that involves a dependent source. So let's first get the circuit that we're going to consider up on the board. We're going to have a capacitor. And let's assume that this capacitor has an initial charge of 10 volts on it. So V0 of 0 is going to be equal to 10 volts. And it's connected to a switch, which closes at time t equals 0. And when it closes, it connects the capacitor to a resistive circuit that has a 10 kilo ohm resistor in parallel with a dependent source, 7I delta, and another resistor of 20 kilo ohms, as so. And I'm going to define the dependent parameter I delta as being the current through the 20 kilo ohm resistor, and the value of the capacitance will be 5 microfarads. And what we'd like to do in this problem is two things. We'd like to find what the time constant is once the switch is closed, and we'd also like to find what the final value of the circuit will be after the switch has been closed for a long time. So let's start with the first problem of finding the time constant. The time constant in a capacitive circuit is equal to the Thevenin resistance seen by the capacitor times the value of the capacitor. So what I mean by the Thevenin resistance seen by the capacitor is you should take the two nodes that the capacitor is tied to and kind of mentally remove the capacitor from the circuit, and the Thevenin resistance that we need to find is basically the equivalent resistance of the remaining part of the circuit. Now in this case, because we have a dependent source, it would be a good idea for us to redraw the circuit and explicitly show the test source that we hook up to it. So let's go ahead and do that now. So let me redraw the circuit now with the test source. So we have some test source VT, and this is going to be hooked up now to the 10K ohm supply. Notice the capacitor, of course, is not in the circuit. Here's our dependent source of 7I delta. Here's our 10K ohm resistor. And here's our 20K ohm resistor with I delta being defined as the current that goes through it. And here's our test current, IT. So to find our Thevenin, now what we need to do is find VT divided by IT. And we just will apply Kirchhoff's laws to be able to do this. So let's first do a Kirchhoff's current law equation at this node. I'm going to define this bottom node as being ground, and if I do that, then this node actually, the value of the voltage is just whatever the test volt source is. So I'm going to directly just label this here as being VT. And if I do the node voltage equation for that node, I can write that IT minus VT divided by 10K plus 7I delta minus VT divided by 20K is equal to 0. And then, of course, I have to define what the dependent parameter is in terms of the node voltage, which in this case is VT. And so I delta is just going to be VT divided by 20K. And if I solve for these two equations, we can find that IT minus VT divided by the parallel combination of 10 and 20K plus 7 times VT divided by 20K is equal to 0. So all I did here was I just substituted for I delta. And now if I solve for IT, I can find that this will reduce to VT times, again, taking the common denominator, 3 divided by 20K And I find that this then reduces to minus VT divided by 5K. So I can take the ratio of VT divided by IT, which gives me a value of R Thevenin equal to minus 5 kilo ohms. Do not let the negative sign alarm you. Because we have a dependent source in the circuit, it's perfectly possible for there to be a negative Thevenin resistance. The only time you should be alarmed is if you have a circuit that's comprised of only real resistors and independent sources, which gives you a negative sign. Because when you have only real elements involved, you should be able to get a real resistance, a non-negative resistance value. Okay, so this is going to be the value of our R Thevenin, and we can just then substitute this back in to our expression for tau, and we would get minus 5K times the value of the resistance, which is 5 microfarads, and this would then give us minus 25 milliseconds. So now you might say, well, what is going to happen to this minus sign? Isn't this a bit weird? So you're right that that does create a certain amount of weirdness. Well, what's going to happen, instead of having a decaying exponential, you're going to have an exponential which constantly rises. So let's see how we can actually now think about this a little bit better. So let's go on to kind of like our other part to the problem. If we now think about what happens in steady state, let's just step through the problem systematically. So if we think about steady state, that will basically help us find our final value. What would we do? We would take the capacitor as being an open circuit, right? And then what happens now to V0 when the capacitor is an open circuit? Well, if there's an open circuit, there can't be any other currents or voltages. Remember that this capacitor is not connected to a source that is independent. So when it's an open circuit, you know, even though there's a dependent source that depends on the other values of the voltage in the circuit, it's not really like a motor in and of itself. So eventually everything will die down, and actually your steady state value for the capacitor voltage is now going to be just 0 volts. Okay. So now let's think about, again, how we can think about this. We can write this circuit as just being the capacitor connected to its Thevenin resistance. Why is that? Well, if you would consider calculating what the open circuit voltage was when you have just a dependent source, you'll find that the open circuit voltage is just 0, and so you're left with a Thevenin representation that's just this resistance, albeit a negative resistance value here. This is our V out parameter that we're trying to solve for, and here's our capacitor C, which is 5 microfarads. And if you go through and you apply KVL and substitute for the elemental equation for the capacitor, you can find that the differential equation for this circuit is dV naught dt minus 1 over 5K times 5 mu, 5 microns, times V out, which is equal to 0. And then if we go through and actually, you know, step through the process of finding the differential equation, what would we do? We would take this term to the other side, divide out by V out and dt, so that we would separate the variables, and that would give you dV out. Let's do some of the intermediate steps. You'd get dV out dt minus 40 V out equals to 0, and then this gives you V out equals to whatever the initial value of V out was times e to the 40t. Okay, and the only reason why I'm kind of redoing this for you is because I want you to show that you still get an exponential as your solution to the equation. Just because your R Thevenin comes out negative doesn't really mean that there's anything different. I'd like you to notice that if you look at the form of this equation, it's still in the form of the initial value minus the final value times the exponential plus the final value. It's just that our final value happens to be 0, and so we're left with this, and then the value of the exponent is positive. We're told at the beginning of the problem that our initial condition was that we had some charge on the capacitor, leading it to having an initial voltage of 10 volts. So we're given this initial condition of 10 volts. And so now we can write the final form of our solution as being V out of t equals to 10 e to the 40t volts. So of course, this is not really a tenable situation, because in real life, if you uncontrollably just continually increase the voltage, then something bad will eventually happen. So right now what I want to do is I want to consider the case to avoid this kind of catastrophic situation where we let V out increase until it gets to a value of 150 volts. And then afterwards we have some kind of fail-safe so that the capacitor is safely discharged through a different resistor perhaps, or removed from the circuit, and so that we have this fail-safe system and the circuit doesn't continually increase uncontrollably. So suppose that when V out equals 150 volts, the capacitor is somehow removed or safely discharged. And what we're interested in is figuring out how many seconds will pass until this condition occurs. So to solve this problem, we need to use the equation that we just found, but this time is going to be our unknown. And we're basically going to solve it by saying that let's find out when 10 times e to the 40, let's call tx, our elapsed time variable, is equal to 150 volts. And if you kind of solve this equation, you can then find that tx is approximately 67 milliseconds. And so it will take 67 milliseconds for the capacitor voltage to rise up to 150 volts, at which time we do something to ensure that this increase doesn't continue and remove or safely discharge the capacitor with some kind of fail-safe system. So I just wanted to show you this example so that you can see what happens in the case where you do have a negative Thevenin resistance that the capacitor is connected to, and how that affects our equation. As you can see, we just applied the same concepts that we've used before. It's not, of course, a very realistic example. We don't usually design circuits to function this way. But again, I just wanted you to see that you could apply the same analysis principles to figure out what happens in the circuit, even in situations where you have a dependent source that causes there to be a negative Thevenin resistance and hence a negative time constant. If you have any questions, please let me know. I look forward to seeing you in our next class. Have a great day. See you all later.